So let me first thank Professor Gifford Vidal and Professor Roger Merkel, Professor Sonsikli for allowing me speaking here. And it's the end of the year, so I appreciate everyone's time and thanks for coming to the talk. I hope I won't disappoint you. So yeah, so the talk is about the theory of a cluster model insulator. So this is the outline of the talk. I'll first provide some motivation and introduction to this work. So then I will explain some the theory of cluster model insulator as well as experiments in 2 dimensions. Then I go to 3 dimensions if I have time. So finally, I summarize the talk. So let me start with a conventional model insulator. So let me first consider triangle lattice Harvard models, single band at half filling. So this is the Hamiltonian. So this would be the expected phase diagram for the single band Hubbard model on the triangle lattice. So when the Hubbard-U interaction is very weak, so the electron just forms liquid metal. So when the interaction, the Hubbard-U is very strong, the electrons are localized on every lattice site. And the Hamiltonian is a simple Heisenberg model. So the ground state is this 120-degree magnetic order state, Berg translation symmetry, Berg spin rotational symmetry, etc. So in the intermediate regime, when the Hubbard-U interaction is strong to localize the electron, but not strong to induce the magnetic order, so it's believed that you have this so-called weak model insulator U1 quantum spin liquid regime. So the underlying physics is as follows. So in this intermediate regime, because the Hubbard-U is not very large, so the charge gap is not very large as well. So then the charge fluctuation is strong. So it will induce long-range spin exchange as well as some like 4-side ring exchange. So these interactions are competing with a near stable Heisenberg model and frustrate this magnetic order and eventually kill this magnetic order in this weak motor regime. So such a disordered regime has been supported by many different numerical methods, and many property of this intermediate regime, spin metal or whatever, so are very similar to electron metal, but with very subtle and important difference because of the presence of a fluctuating U1 gauge field. So the low energy effective field theory for this intermediate regime U1 quantum spin liquid is described by a spin-on Fermi surface coupled with a fluctuating U1 gauge field. So this is a strong coupled theory, and so the property of this so the understanding of this field theory is very hard. There is no controlled method so far. There are some attempts, but it hasn't been resolved yet. What? Sorry?
What is the strongest evidence for the spin liquid phase?
Yeah, so I mean there are numerical evidence and experimental evidence. So let me provide the experimental evidence.
No, but numerical, because I mean you have because experimentally probably it's not exactly this model, right, that you're talking about. But let's say if you're talking about the model.
Yeah.
Right, so what is the strongest numerics?
I see. So there are DMRG results on this some fat ladder. Then also exact diagonalization, but it's a small system. So people also look at effective model. Instead of looking at the Hubbard model, they look at Heisenberg spin model. So they consider a Heisenberg model plus a ring exchange. So they consider some near stable Heisenberg model plus a 4-side ring exchange, and they change the parameter and look for whether there is a quantum spin liquid regime appears when you tune some coupling parameters.
Right. But that model is not equivalent to the Hubbard model.
Right. So, yeah.
There's some DMFT as well.
Yeah, DMFT. Yeah, but DMFT, yeah.
I mean, it's approximate method,
sure.
But I mean,
Yes.
I think the exact analyzation on the quantum coupling expansion for the continuous regime sees that when you reach about U of the T of order 12 or so, you see a proliferation of singlets in the singlet in the triplet gap. You might think that this is really a precursor to this way. You just see all these singlets crashing down.
Right.
Yeah, I agree with you. I mean, every numerical has its own problem, and this is a gapless state, so it's very hard to detect. For gap, it's relatively easier. So yeah, so let me. So far there are 3 organic compounds. They are being proposed as candidates for triangle lattice Huffman model spin liquid. So these first 2 guys are the old ones. There is a recent new ones is discovered this year. And so in this kind of system, so the electron are localized on some kind of molecular dimer. So the electrons are shared by these 2 dimers. So if you view this dimer as a supersite, these supersites, they themselves form a triangle lattice. And each side has a spin 1/2 moment. So that's the spin 1/2 triangle lattice. So they did a very careful measurement. At high temperature, you get some QUS law. But at low temperature, at low temperature, the spin susceptibility deviates from the QUS law. And in fact, if you look closely, and at 0 temperature limit, the spin susceptibility become a constant. So this is very much like a poly-like spin susceptibility in liquid metal. So there are also many other measurements besides this thermodynamic measurement. There are transports in these 2 compounds. So my focus today is not on this kind of material. So let me go back to this first diagram. So it is now in this regime, the presence of, if it is present, this U1 spin liquid, if it exists, it's because of strong charge fluctuation in this weak model regime because charge gap is small. So I want to make a few remarks on the mechanism, physical mechanism for this quantum spin liquid instead of a physical property of this quantum spin liquid. So in fact, there is no sharp distinction between the charge fluctuation in this weak model regime and strong model regime, despite that there are different spin phases. So the second remark is the charge fluctuation being strong in this intermediate regime, in the weak model regime, is only a quantitative description of the charge fluctuation. It's not a qualitative description. So I want to raise the following 2 questions or 2 observations. So yeah.
I don't think it's known, but you can imagine that the double occupancy fraction would have a discontinuous first order jump as you move from the strong limit to the...
Yeah, but it's still...
That's quantitative, you would call this quantitative.
It's still quantitative, right? Yeah. So yeah, I want to raise these 2 questions or 2 observations, if you like. So what if the charge fluctuation is very strong? So according to this argument, the charge fluctuation, strong charge fluctuation favor quantum spin liquid. Suppose I make the charge fluctuation being very strong, and in the most extreme case, suppose the charge sector form a quantum charge liquid, that's very strongly fluctuating. And according to this argument, the spin sector should be even more likely to be a quantum spin liquid. So this is the first observation based on this understanding of this phase diagram. So the second question, the second observation is, what if the charge fluctuation lead to some kind of structure in the charge sector? Spin sector will surely be influenced by this charge structure in a very non-trivial way. And this will lead to a very striking experimental consequence. And if this experimental consequence is being observed in real experiment, they will give us lots of confidence on the theoretical framework we're developing. So these are two questions I'm going to answer or address in this talk. So these two questions has one physical answer, and which is a cluster model insulator. So cluster model insulator is a new class of model insulator. In cluster model insulators, the electron actually doesn't matter whether the particles are fermionic or bosonic. So the particles are localized on some cluster unit instead of lattice site, and these cluster units build up the lattice. So my goal of this talk is to introduce the notion of cluster model insulator. So these cluster model insulators that are interesting and they exist in nature. Actually, quite a lot of them. I guess many organics are cluster model insulators, and they haven't been studied before. So the second goal is molecular orbitals.
You mean like if I have these molecules that build material and electrons that move around this molecule, that's a cluster.
Yeah.
That's what you mean.
Yeah. So I want to develop a new theoretical framework to understand the node charge fluctuation and the spin fluctuation in cluster model insulator and apply it to illustrate the examples and explain the puzzling experiment. So I'm going to the two-dimensional cluster model insulator. So I was saying I was talking about striking experiment. What is the striking experiment? So this is the striking experiment described by Tara McQueen at the Johns Hopkins University in this material, lithium zinc molybdenum oxide. So in this material, it's called a triangle lattice of triangle cluster. So these molybdenum, these green are molybdenum atoms. They form a triangle cluster. These triangle cluster, if you view this triangle cluster as a supersite, these supersites themselves form a bigger triangle lattice. So in each triangle cluster, there is a one unpaired electron. So this electron is localized in this inside this triangle cluster. They form a local spin 1/2 moment. So naively, you would think this system is described by triangle lattice spin 1/2 model, because the supersite form a triangle lattice. There is a one spin 1/2 moment here. So surprisingly, they measure the spin susceptibility in this material. So at high temperature, you get a well-defined Killy-Weiss law. So at around 100 Kelvin, they said there is a turning point. The slope of this spin susceptibility, inverse spin susceptibility versus temperature is changed. So if you look at carefully, the slope of this one is exact 3 times of this one. And the slope, well, according to Killy-Weiss law, the slope is the inverse of the Curie constant. The Curie constant measures the number of active spin moments. So that means the number of active spin moments at low temperature is exactly 1/3 of the high temperature ones. So this is very, very striking. Moreover, the Curie temperature is significantly reduced compared to the high temperature Curie constant. It's about the factor of 10 difference, or 1 order magnitude reduced compared to high temperature. So why it's striking and difficult? So if you view the system as the triangle lattice Heisenberg model, and in the spin 1/2 and the triangle lattice Heisenberg model, the system should order, and there is no such fractional spin susceptibility. And if we view the system as triangle lattice Hubble model at half filling, we also don't have this. We don't have fractional spin susceptibility, and spin susceptibility should become a constant, just like organics. So neither model applies to this system and cannot explain the experiment. So actually, this 1/3 fractional spin susceptibility has some, I think it's interesting because it has some similarity with this 1/3 Laughlin state, fractional quantum Hall Laughlin state. Xiaogang is not here. Xiaogang described 1/3 Laughlin state as all the electrons in the Laughlin state are doing some kind of collective dancing under a rule, so that every electron moves 3 steps around the other electron in the lowest random level. So the electron in this material, is there any collective behavior associated with the electron in this material? Actually, there is some similarity, and I will explain the similarity here. So first, let's look at the structure more closely. So in fact, the system is, the people say it's a triangle lattice of triangle cluster. In fact, if we connect them, it's a Kagame lattice. It's not it's a triangle lattice of triangle cluster, but in fact it's a Kagame lattice. Just these green triangles and the red triangles are of different size. They're slightly different. It's anisotropic triangle lattice. So that's an important step, in fact. So the claim, my claim is the system should be described by a single band extending the Hubble model on an anisotropic Kagame lattice with 1/6 electron filling. Because for each triangle cluster, this solid triangle cluster hosts one unpaired electron. And one electron shared by these 3 sides. So if you count the spin degeneracy, that's 1/6 electron filling. And the minimum model allowed by symmetry actually is this extended Hubble model. And it's, in fact, it requires some quantum chemistry to obtain this model. And it's very important to how to arrive this model from quantum chemistry. And there's some physical argument beneath it. But for the purpose of this talk, I will not talk about too much about quantum chemistry. So let's just believe this model describes this system. So this model has 5 different parameters. So the first is so on this solid triangle. So there is a hopping, nearest neighbor hopping between 2 sides, and there is a nearest neighbor repulsive interaction. If there are 2 electrons occupy these 2 sides, then is a nearest neighbor repulsive interaction. And similarly, on the dashed down triangle, there is a nearest neighbor hopping T2 and nearest neighbor repulsive interaction V2. And besides these 4 parameters, we have on-site Hubbard U interaction. And the physical, so Hubbard U, large Hubbard U cannot localize the electron because the filling is not half filling, it's fractional filling. So we need a nearest neighbor repulsive interaction V1, V2 to localize the electron. If we only have Hubbard U, the electron can still move around. I mean, Hubbard U just kill double occupancy. It doesn't localize the electron. So V1, V2 are needed. First of all, it's because of molybdenum is a 4D electron. So the wave function is extended. So we need to consider this extended interaction. So this is the genetic phase diagram. So I will explain how to obtain this phase diagram. But first, let me explain the property of different phases. So Hubbard U is always large. It doesn't. We said our Hubbard U to be very large, so we don't care Hubbard U. This Hubbard U doesn't enter into this Hubbard phase diagram. So suppose both interactions are very weak. So the hopping term dominate. So the system in a Fermi liquid. So interactions are very small. Now suppose we increase the interaction V1. V1 is the interaction on the solid triangle. So if we increase the interaction V1 but keep the V2 to be small, if we go along this direction. So the interaction on the up triangle is very strong. So it localizes the electron on the up triangle. So the electron number on the up triangle is fixed to be 1. But the electron number on the down triangle is still fluctuating because V2 is small. It doesn't cost too much energy to place 2 electrons on the down triangle because it doesn't cost too much energy. V2 is very small. So in this regime, so I call it a type 1 cluster model insulator up. So electrons are localized on the up triangle. The electron number on the up triangle are fixed. So that's the insulating state. So similarly, if I increase V2 but keep a V1 small, so the electron will localize on the down triangle. So this type 1 down. So suppose if I increase both V1 and V2, make both of them large, so then the electron should be localized on both up and down triangles. The electron number on the both up and both down triangle will be fixed to be 1. So a simple understanding is electrons are localized in one type of triangle in a type 1 cluster model insulator, and electrons are localized in both type of triangle in a type 2 cluster model insulator. So what is a type 2 cluster model insulator? So electrons are localized on both up and down triangles. So electron number are fixed to be 1 on both up and down triangles. So but electron position are not frozen. So this snapshot of electron configuration on this David star shape. So there are 3 electrons. They should be away from each other. If this electron is here, this triangle is not happy. So but electron can still doing some move, can still doing some collecting move. There's this quantum mechanical process is allowed. So suppose this electron moves to here. So then this triangle is not going to be happy because there are two electrons here. So then this electron must escape to somewhere else to avoid this electron. So if this electron moves here, and this triangle is not going to be happy because there are repulsive interactions here. So then this electron must escape. The only way to escape is to this side because this side is already moved away. So this is some kind of third order process in type 2 cluster model insulator. So this is some kind of resonating process. So this thing can be mapped into a dimer resonant. If you map this occupied electron side to a colored link, to a dimer link connected in the center of 2 nearby triangles. So this configuration, this electron configuration mapped to this dimer configuration, and this electron configuration mapped to this dimer configuration. So this third order process is called a dimer resonating process. So the correlated electron motion on the type 2 cluster model insulator is mapped to a dimer resonating on a dual honeycomb lattice. If we connect the center of each triangle, they will form a honeycomb lattice. It's a dual honeycomb lattice. So the low energy for the effective model is a quantum dipole model on a dual honeycomb lattice. So this is the charge sector low energy Hamiltonian in the type 2 cluster model insulator. So in fact, it's well known that the quantum dipole model on a bipartite lattice can be mapped into a compact U1 gauge theory, like on a honeycomb lattice. I mean, Fredkin and Kilverson, they did on the square lattice, so which is bipartite. So this is the honeycomb lattice. It's not very different. So because of there is the underlying gauge structure in the charge sector already. So if we want to study the approximate phases of the type 2 cluster model instead, if we view the type 2 cluster model as the parent state and try to obtain the nearby phases from the type 2 cluster model insulator, so we need to invent a new parton gauge construction to describe the phase transition. So originally for conventional model insulator, we have this kind of slab rotor construction. We decompose the electron into its charge part and its spin part. The spin part carry fermionic statistics, and the charge part carry electron charge. So that's the original slab rotor construction. It works for the conventional model insulator spinning grid. And the internal gauge structure is a U1. I add a subscript SP, means a spin-on. Okay, it's a U1 spin-on gauge. Then the U1 gauge structure because of this gauge redundancy. So for the cluster model insulator, the parton gauge construction need to take into account the fact that we have an additional gauge structure in the charge sector. So we need to, in addition to write down the electron into a charge rotor times the fermionic spin-on, we need to further decompose the charge ions into two parts. Because adding a charge here create violate the localization condition on both up and down triangles. That's like adding a gauge charge onto the up or down triangle. So we need to decompose the electron into this kind of thing. So we decompose the electron we fractionalize the electron into three parts: one fermionic spin-on and two charge ions. So this is a new type of parton construction to capture the two U1 gauge structures in the theory. There is a U1 gauge structure in the charge sector and a U1 gauge structure which causing the spin charge separation. So now I want to make a digression a small digression. So there are, as pointed out by Song-Sik Lee to me, so there are two classes of parton gauge construction, two parton gauge theories in quantum magnetism. So the first type of parton gauge construction was introduced by the slab fermions is introduced by Ian Affleck, and then is a bosonic spin-on introduced by Sybil Sachdev, and also this slab rotor construction. So this kind of parton gauge construction are often blamed to be unjustified, and it's often hard to develop a physical intuition and to cut the spin into two pieces and glue them back by gauge field. So it's very hard to develop some intuition, but it works sometimes. So there is actually the second class of parton gauge constructions. So in this kind of parton gauge construction, the second type of parton gauge construction applied to the cases where the microscopic model at the low energies or at the intermediate energies already looks like a gauge theory. For instance, in my case, this charge sector quantum dipole model is already like a U1 compact U1 gauge theory on the honeycomb lattice. So also negatory quantum model is like a gauge theory already in the square lattice. So this kind of the second type of Parton gas construction was developed by Oleg Cheryshev on the Kagami lattice, lead to spin liquid, and Leon balance on this quantum spin ice system. So the Parton construction I used here is a combination of these two type of Parton gas construction. So I use in the charge circuit, I use this type of Parton gas construction. So that's the formalism. I mean, I write the microscopic harmonic can be translated into this lattice gauge theory, and it can be decoupled into a charge circuit, a spinel circuit, and a gauge circuit, and can be solved self-consistently. And then how do we obtain the first diagram from these mean field solutions? So in a forming liquid metal, the electron number on both upper and down triangle are strongly fluctuating. So that means the charge boson living on the upper and down triangle are condensed because the charge number are strongly fluctuating. So both of them are condensed. So the U1 gauge field in the charge sector is Higgs, and similarly U1 gauge field in that lead to spin charge separation is also Higgs. So in a type 2 cluster model insulator, this is the type 1 cluster model insulator, the electron number on the down triangle are strongly fluctuating, but the electron density on the up triangle are fixed. So that means the charge boson on the, this should be reversed actually. The charge boson on the down triangle are condensed, but the charge boson on up triangle is not condensed. So because the charge boson is condensed, the U1 charge gauge field is Higgs, but the U1 spinel gauge field is not fixed. It is not Higgs, it's deconfined because of the presence of spinel Fermi surface. Similarly, on the type 1 down cluster model insulator. In type 2 cluster model insulator, the both up and down triangle electron density is fixed to be 1. So then the boson, the charge boson, either charge boson is not condensed, none of them is condensed. But the U1 gauge field, that causes spin charge separation is still deconfining because of the present spinel Fermi surface. So what's the property in the type 2 cluster model insulator? So in fact, the quantum dipole model on a honeycomb lattice has been simulated by Ludwig Mott and Sondi and Chadra like more than 10 years ago. So I couldn't find a photo of her. So it has been. I mean, they look at a very generic, a very general quantum dipole model. Besides the dimer resonance term on the hexagon, they also include the potential energy term for the dimer carbene. So our problem corresponding to V equal to 0, where there is no potential energy term. So this is the first diagram. So our model will be here. So that means our model should develop this kind of placated dimer pattern. So this placated dimer ordering means the dimers are preferred to resonating on this broad hexagon. It breaks translational symmetry instead of on the thin gray hexagons. So if I translate this dimer language into my electron language, so that would be the charge occupation configuration in this placated charge ordered phase, or in type 2 cluster model insulator. So in this phase, the translational symmetry is broken, and the 3 electrons are preferentially resonating on this hexagon, which has a circle in it, and it's either this configuration or that configuration. In fact, it should be thought as a linear superposition of these two configurations. I mean, it's hard to write linear superposition with figures. So this is a quantum mechanical effect. That's not a classical result. It's a quantum mechanical effect. It's a linear superposition of these two, and it's this placated charge order. In a sense, it's a charge RVB. It's a resonant valence bond, but it's in a charge circuit. It's a local RVB. It's not global RVB. It's local in this cluster, in this hexagon. It's a local, Professor Anderson RVB, but in the charge sector, not in the spin sector. So it's a collective behavior. It's a collective behavior of 3 electrons, 3 neighboring electrons on this hexagon. It's a local collective behavior. The electron motion always avoid each other, but they're doing some kind of this collective behavior together. 3 electrons are doing this kind of dancing on this hexagon. So it's a quantum mechanical effect. So that's the charge circuit physics in the type 2 cluster model insulator.
Sorry, excuse me.
Yeah.
So how many ground states are there? 2?
How many ground states?
Yeah, in this
model.
In this phase, yeah.
In this phase, well, we only have 1. So our model would be this red dot. We don't have this V term. We don't have potential energy term.
Except for the degeneracy coming from symmetric breaking.
Yeah, that would be 3.
There's only 1 ground state.
Yeah, if you count the symmetry breaking, that will be maybe 3 states.
Okay.
Because this one can be here or here, right?
Oh, okay.
So that's 3. But yeah. So that's the charge sector physics. So so when I wonder how does the charge sector influence this the spin sector, as I said in the beginning, if the charge sector develops some kind of structure, it will surely influence the spin in a non-trivial way. What's a non-trivial way in this spin sector? So I think a couple of weeks ago, Sid from UC Irvine gave a very nice talk about this Lipschitz-Mellers theorem, or she called it Hastings theorem. So this theorem states that for a model insulator with odd number of electrons per unit cell, it's either topological or gapless. Right? That's the statement of the theorem. So in a type 1 cluster model insulator where there is no symmetry breaking, there is 1 electron in the Kagami unit cell. So that's a spin grid. So now we are in a type 2 cluster model insulator. In the type 2 cluster model insulator, the translational symmetry is broken and the unit cell is tripled. So that this dashed black triangle is the new unit cell. So it contains 3 electrons, and the 3 electrons are doing this resonating thing inside this hexagon. 3 is also odd number. So that means according to this theorem, it's a spin grid. In fact, we can look at how does the plaquetted charge order influence the spin-on band structure more precisely. So that's the Briand zone of the type 1 cluster model insulator where there is no symmetry breaking. So with symmetry breaking, the Briand zone is reduced. Actually, only 1/3 of the size of the bigger Briand zone of the type 1. So the dashed one is the type 2 cluster model insulator unit cell. So if we look at the spin-on band structure, so if there is no plaquetted charge order, so if we there will be, because this Kagami lattice has 3 sublattices, and there will be 3 spin-on bands, and because of fractional filling, we can forget about up 2 bands. We only focus on the lowest band. The lowest band is partially filled in the type 1 cluster model insulator. So if we fold the band structure onto the type 2 cluster model insulator Briand zone, we get this kind of band structure, and this is doubly degenerate. So now we introduce a plaquetted charge order. So this doubly degenerate band structure will split. Will start to split, and then they open up a direct band gap. If I further increase the plaquetted charge order, so the direct band gap becomes bigger and bigger, and eventually the lowest band will be completely filled. If you count the number of spin-ons, like 2/3 of the spin-on will completely fill the lowest band, and 1/3 of the spin-on will partially occupy the up 2 bands and form a spin-on Fermi surface. So that's the ground state property. So now what's the implication for the spin stability from this band structure and the filling? So as I said, if we increase the temperature, if we add some finite temperature, so a fully filled band, this band is fully filled. A fully filled band is in active inertia to external magnetic field. It doesn't respond to external magnetic field. We can basically forget that this completely filled band and throw them away. Only look at the spin degrees of freedom on the partially filled band. So there are exactly 1/3 of the total number of electrons in the up partially filled band. At finite temperature, this 1/3 of electron will contribute to the 1/3 spin sensibility, 1/3 of the Curie constant at finite temperature, at a low temperature. So that will explain why there is a 1/3 spin sensibility anomaly at low temperature. The Curie constant, measures the number of active local moments. So the moments is only 1/3 of the total number of electrons here. On the other hand, the bandwidths of this partially filled band give you an estimate of the Curie rise temperature at low temperature. So the bandwidths measures give you estimate of the Curie rise temperature. Without the plaquetted charge order, the bandwidth is large. This would be the bandwidth, effective bandwidth. Now, if we increase the plaquetted charge order, this band is completely filled. It doesn't, it's inactive to the magnetic field. Only these bands are active. The effective bandwidth measures the Curie rise temperature. So this tell us why this Curie rise temperature is very small at low temperature. So this is the understanding from spin-on band structure reconstruction when the plaquetted charge order is present. So we can also look at the spin sector differently from a different point of view. By the way, is there any questions?
Why the particle field spin-on band didn't try? Why not give you the from liquid behavior?
Yeah, that's zero temperature limit. It will give you constant spin sensibility. Just like organics, at low temperature, at the zero temperature limit, we get a constant spin sensibility.
Yes.
But if we increase the temperature, then it's a crossover.
So you are in the high temperature limit.
Sorry?
So you are in the high temperature limit.
Yeah. Okay. So another view is from the spin state reconstruction. So in each unit cell, there are 3 electrons. There's 3 electrons that are doing this collective dancing inside of this hexagon. So 3 electrons, if we, from simple quantum mechanics, 3 electrons are, each of them is spin 1/2. From the spin composition rule, we can either have like a total spin 3/2 or spin 2 spin 1/2. So in order to have a spin 3/2, we need a very strong ferromagnetic interaction. So that's not going to be favored. So it doesn't really enter here. We can just forget about this spin 3/2. So the only 2 possibilities are these 2 spin 1/2. And so that means there are 4 degrees of freedom here. So 1 spin 1/2 degrees of freedom corresponds to real spin 1/2. Then which spin 1/2 is picked? That will correspond to a pseudo spin 1/2. So that's a non-magnetic moment. So when you so that's the understanding from the spin state reconstruction within one unit cell. So within one unit cell, there is a spin 1/2 and pseudo spin 1/2 moment on each big unit cell. Then these unit cells themselves are coupled in a, these circles, these 3 electrons in each these red circles, they are coupled in a way. So the effective model to describe the interaction is a Kugel-Komorowski model because we have a pseudo spin 1/2 and a spin 1/2. One can actually write down the model, derive the model, and because 3 spin 1/2 electron, they effectively behave like a 1 spin 1/2 local moment. So that will naturally explain why we have 1/3 spin sensibility anomaly in the low temperature. So that's the one more physical explanation in terms of spin state reconstruction. In fact, we can compute this Curie rise temperature, then the reduction of factor of 9 here. This reduction is due to reduce the probability of spin interaction, because originally each spin can interact with its neighbors, but then after they form this superposition state, the probability to have this interaction is reduced. So I want to give a summary on this material. Yeah.
So you say this is another view.
Yeah.
Okay? And then this seems to be much simpler, right? And it's quite natural, right? So why did you need the first part which was not very complicated?
Yeah, so that's a good question. So from this kind of view will give you a faculty Hamiltonian, but then it's hard to obtain the spin-on band structure. So if one want to compare with neutron scattering, index the neutron scattering spin structure factor, one need to rely on spin-on band structure and compute the thing.
So you're saying you would take this model that you derived, which is, but now it's a spin-on half model, right? Nothing.
Mm-hmm. I think the misunderstanding is so in the usual triangle lattice case, we have Hubbard model. Intermediate regime, we should use Hubbard model. In the strong coupling regime, we should use Heisenberg model, use the local moment description. So here, if the electrons are strongly localized inside this hexagon, then we'd better use in this local moment point of view, spin moment reconstruction point of view. But if the electrons are not that strongly localized, in a sense, in an intermediate regime, so then we'd better use a spin-on band structure picture.
Even though it's also, of course, it's controlled, right? And experimentally, in principle, it's not like we have any strong hint that we should do that. Right?
Yeah, experimentally, we don't have a sense of what's the number of charge gap. We don't really know the charge gap. But both of you give me right prediction on the spin susceptibility, right?
Your experiment can't tell the difference between these spin 1/2s are localized on those plaquettes versus ones that are forming in terms of this spin.
So experimentally, how do I tell this?
Just this particular experiment that you showed, just the 1/3.
Yeah.
That does not tell the difference between a spin 1/2 that's localized on these plaquettes versus. Is that right? So in your spin reconstruction picture.
Yeah.
Suppose I just said the effective Hamiltonian was 0, I would still get the same susceptibility.
Yeah. So yeah, I suspect because this Kugal-Komorski model, one cannot solve this model. It's a very frustrating model. The ground state is likely to also be a spin liquid, and it's likely to be smoothly connected to the intermediate regime U1 spin liquid. But this thing cannot be solved. So. Yeah, I mean, one can use partons, use slab fermions, doing some machinery calculation, but it's not. I mean, one shouldn't. It's very hard to develop intuition, as I said. Yeah.
In the neutron data, do they see the spinor anti-spinor spec continue?
Yeah, let me come to this in a few slides. Yeah.
So, what about coming back to Venetia's question? What about the local flow measurements like NMR?
Yeah, so it will come next slide. Sorry. Yeah. So let me summarize this simple picture. So the emergence of the plaquetted charge order is the driving force for the 1/3 spin susceptibility anomaly. And in fact, if I use the fancy language of PI, this is the short-range quantum entanglement to create this 1/3 spin susceptibility anomaly. And the spin ground state is a U1 spin liquid spin-on Fermi surface. That's a long-range quantum entanglement. So that's the pattern of short-range entanglement, if you like. So that would be some kind of some schematic phase diagram. Because the plaquetted charge order breaks translational symmetry, so there must be a finite temperature phase transition at some finite temperature. And it will finite temperature, then you get a different Curie-Weiss law. Actually, this is consistent with experiment. I mean, there is a finite. One should interpret this turning point as a finite temperature phase transition to destroy this finite phase transition. Destroy the plaquetted charge order, and you go back to the type 1 type of behavior. And in fact, they measure heat capacity, magnetic heat capacity. There is a peak around 100 Kelvin, which is the turning point of this spin susceptibility. So this coincides with this peak. But this heat capacity peak is very broad. It's probably due to charge disorder because there are so many lithium here. Lithium is very mobile, create a charge disorder. So the first transition is I expect it to be a first order finite temperature first transition.
Why is it first order?
Because it's a tripling of unit cell. If you write down a lambda theory in terms of order parameter, there will be a phi cubed term.
What is in 2D?
It's
also the parameter type?
No, this is 2D, but it breaks a discrete translational symmetry. It's not a continuous symmetry breaking. It's discrete lattice symmetry. So, right? It's not a continuous symmetry, so there should be a finite temperature phase transition. It's not clear?
Yeah, I understand that. Yeah. But what's the order parameter symmetry? Isn't it?
The order parameter is the charge density wave. If you, I mean, this placket charge order is
three equivalent symmetry equivalent discrete states, right?
Yeah.
So it's
just electron density.
Yeah. So what's the order parameter? Like, is that three theory, or is it like plots? A three-state plots type order parameter?
Yeah, it's like that, but there is a 5-cube term in the theory because of tripling of unit cell. Usually, I mean, in the coarse-grained description, I write the density in terms of, phi times I, some q times r. Right? Is it clear? No? No. Yeah, maybe we can talk after.
Well, it's always going to be first order. I'm just thinking that if it's plots in 2D, could easily be second order. Mm-hmm. Because 3 says plots in 2D is second order.
Mm-hmm. Yeah. Okay. Well, I don't know about this.
Well, there's a cubic invariant.
There is a cubic term.
Invariant in the 3-state plots not in 2 dimension. Yeah, the transition is second order.
Mm-hmm. I see. I didn't know this fact actually. It's nice to know. Thanks. Yeah. So prediction. So in the charge sector, we have this, first order transition. Okay. So what's the other prediction for the spin sector? So the ground state is expected to be U1 spinning with a spin-on formation. We have this 2/3 heat capacity and chi constant at a very low temperature because the QE temperature is very small. So in order to see this, you need to go to very low temperature. Spectroscopically, on MR, measure this 1/T1T, spin lattice to relaxation time. So this is proportional to density of state. Because of the reduction of the spin-on bandwidth, the effective density of state is enhanced at very low temperature. So that's why there is a big peak at the 1/T1T measurement. And neutron scattering is not particularly conclusive because of very poor resolution. So the experimentalist claim is a gapless spectrum, and it's consistent with the spin-on Fermi surface picture. But it's very hard to obtain some structure from this current data.
You read the charge.
Yeah.
So what did you say about the peak, that it was because of disorder?
Yeah, so if first transition would already imply a peak. But if there is a disorder, the peak is broadened by the charge impurity, by the charge disorder.
But how do you think this would affect the spin? Like if the spin field is so tight to the charge, this nice ordering of the planet.
Yeah, so in fact, if you look at the spin susceptibility data, actually there's some noisy up here. There's some noisy up here. I mean, I don't know. So I predict that this material is type 2 class model insulator. So where is the type 1 class model insulator? So in fact, this material, this molybdenum class model insulator is represent a big class of physical system, and the electron are localized on some cluster. So this material, this lithium indium molybdenum oxide, there is no spin susceptibility anomaly, and at very low temperature, the spin susceptibility almost become a constant. At a very low temperature, there is a sharp peak as due to impurity. So that's actually compatible with this material being a type 1 class model insulator. But there is very limited experiment. I can't tell you too much about this. So I have another 10 minutes. I think. So I will go quickly on the theories of 3-dimensional class model insulator. So before I go to this topic, is there any question on the 2-dimensional class model insulator?
Do you have a log correction to the t to the 2/3?
No, that's due to the self-energy of the spin-on is omega 2/3.
But from an experimental prediction, right? T to the 2/3, if there's no log correction, could be exposed, right? The log t is going to screw up.
Yeah, if you measure CV over T, measure the gamma factor, then it's a divergence. But it's very hard to measure. In fact, even in the organics, which has a higher energy scale, 100 Kelvin spin exchange, it's very hard to see this T to the 2/3 behavior. So yeah, I'm not quite sure. Whether this thing is easy to observe or not.
But this is different because you're in the low temperature regime once all the phonons are gone, you're below 2 Kelvin.
Mm-hmm.
So this is a cleaner case than the organics.
Yeah. But there is some. Well, yeah, at a very low temperature, the nuclear spin kicks in. So the nuclear spin will when you get a Shockley anomaly, will pollute your data. So at a very low temperature. Yeah, this is always the issue. Why similarly in quantum spin ice, which would require very, very low temperature to see the quantum mechanics. But at very, very low temperatures, other effects kicks in, messed up with the data. So I expect the similar things will happen here. At a very low temperature, some for instance, the nuclear spin Shockley anomaly will appear in the heat capacity data, and will cover up this kind of intrinsic behavior of quantum spin liquids, for instance. Yeah.
Why? If it's a spin liquid, there's no mean amplifying fraction. So how do you get the nuclear anomaly when you are in a spin liquid?
Well, nuclear spin is the degrees of freedom. So if you measure heat capacity, it will always contribute to your, unless you have a way to subtract the contribution properly. Otherwise, it's very hard to do it. So let me slightly explain some more motivation about three-dimensional cluster model insulator. So there is a intense theoretical and experimental activity in quantum spin ice and classical spin ice. I think Professor Michel Gingras is an expert on both fields. So there are lots of material actually. So last year when I was working on symmetry enriched quantum spin ice, so we know that this particle material system is an F electron. So the exchange interaction energy scale is very low. So in order to see the intrinsic quantum mechanical behavior of quantum spin ice, one need to go to very, very low temperatures. And as I said earlier, at a very low temperature, many other effects kicks in and make the interpretation, make the data very difficult. So is there any other alternatives? So there are two alternatives question one can ask here, or motivation. So can we use other degrees of freedom to reveal the quantum spin ice physics? So as we condensed matter physics view, in our condensed matter physics view, electron is a combination of spin, charge, and orbitals. So if we use a spin degrees of freedom, we get a quantum spin ice. That's the most famous case. In fact, the quantum spin ice is a combination of spin and orbital because of spin-orbital coupling in F electrons. So the most famous example is quantum spin ice, use the spin degrees of freedom. So if we use the charge degrees of freedom, we will get a quantum charge ice. So this is the rest of my talk. So if we use orbital degrees of freedom, we get a quantum orbital ice. It's an unpublished work of mine. Quantum charge ice?
Yeah, because the protons can tunnel on different positions. I think there are some papers claim that.
There's some people claim that. Okay.
That the water ice quantum charge ice.
Yeah. So the charge are interacting with a much higher energy scale than the F electron spin. So presumably one can observe this physics at a relatively higher temperature. So there is another very non-trivial question in my mind, I think. So is there any other physical observables that do not have a strong temperature constraint, but still in the quantum spin ice materials, but still manifest the intrinsic property of quantum spin ice? I think this question is very non-trivial, and this is a work in progress. I can't tell you too much about it. So yeah, so three-dimensional cluster model insulator as a manifestation of quantum charge ice. So I consider this kind of extended Hubble model, which is similar, but preserve the inversion symmetry of the particle lattice. This is particle lattice. It's called shared tetrahedral. In a large U limit, which only allow single occupancy or zero occupancy. So at 1/4 filling, if the interside repulsive interaction is very strong, the electron will be localized in the tetrahedron. There will be 2 electrons in each tetrahedron. If I map this occupied side as a spin pointing out of the tetrahedron, and unoccupied side as electron as a spin pointing into the center of the tetrahedron, this charge localization constraint will be mapped into a 2-in-2 out spin ice rule. So because the equivalent spin ice Hamiltonian, effective spin Hamiltonian, will support the quantum spin ice phase, that means the charge sector of the problem will support the quantum charge ice phase. In other words, the charge sector is equivalently a Coulombic charge liquid. It's a quantum charge liquid. So in this interesting phase, the low energy physics of the charge sector is described by immersion compact quantum electrodynamics in 3+1 dimension, and the charge excitation will carry 1/2 of the electron charge. So in fractional quantum Hall is the example have charge fractionalization. So this is another example of charge fractionalization. So the electron is fractionalized into 2 charge zones and one spinons. And there are 2 U1 gauge fields here. 1 U1 gauge field in the charge sector, 1 U1 gauge field that causes spin charge separation, that both are deconfined. So not only this phase is interesting, the Mott transition is also very interesting. In order to get the Mott transition, we need to condense the fractionized the charge zones at the critical point. And when the fractionized charge zones are condensed, so both the U1 charge sector gauge field and the U1 gauge field that causes spin charge separation are also Higgs. So one can actually use in the real light X-ray scattering to probe the internal immersion the U1 gauge field in the charge sector, because X-ray measures the electron density. So using if the inelastic X-ray scattering measures the electron density collision. So the density collision will have this kind of immersion the gauge photon kind of spectrum in inelastic X-ray scattering. At high temperature, if we kill the quantum mechanics, one can obtain some classical charge ice. We can go to this similar pinch point, just like a classical spin ice have. So the Mott transition is very interesting. The low energy effective field theory is described by 2 charge zones and 1 spinons minimally coupled to 2 U1 gauge field instead of just 1 U1 gauge field. So the dynamical scaling exponent for the charge sector is Z equal to 1. The dynamical scaling exponent for the spinon sector is Z equal to 3. They are very interesting. There are 2 different crossovers controlled by charge sector and the spinon sector, and they lead to some interesting thermodynamics and transport phenomena. In fact, the real material is a superconductor actually. So the proximity metallic phase is a superconductor. So actually superconducting is very interesting. So in fact, if it is superconductor, so there is some interesting possibility that both U1 charge sector gauge field and U1 spinon sector gauge field, they can be both Higgs down to Z2 gauge field instead of just the continuous part can be Higgs in the motor insulating phase. So the resulting cluster motor insulator can be Z2 quantum charge liquid plus the Z2 quantum spin liquid in 3+1 dimension. So this is the one direction I'm pursuing right now. So I want to summarize the talk. So I propose these 2 questions in the beginning of the talk. What if the charge fluctuation is very strong and in the most extreme case, the charge sector form a quantum charge liquid, which is the 3-dimensional cluster model insulator. The charge sector is a quantum charge ice or Coulombic charge liquid. So the other question is, what if the charge fluctuation leads to some structure in the charge sector. So that's the two-dimensional cluster model insulator, which apply to this lithium zinc molybdenum oxide material and lead to some striking experimental consequence. To summarize, so I'll provide two specific examples about the physics of cluster model insulator. And there is an interesting interplay between a charge and a spin degrees of freedom in both two-dimensional and three-dimensional cluster model insulator. So cluster model insulator are new physical systems that may host various emergent and exotic physics. Yeah, thanks for your time.
So could you please go to the slide showing the molybdenum oxide? So can you show the specificity? Sorry, the sensibility data? Yeah, right. So this one. So I guess one of your motivation is to explain this 1/3 downturn behavior. So have you thought about more conventional explanation for this? I'm asking this because it seems to me that if there is such a state where you have those plateau order, charge order, then you necessarily break the translational symmetry of the lattice. So I guess one mundane mechanism which has this symmetry breaking is that just imagine all those. So there is a trimerization of those spin-1/2 spins. So there is no charge dilution involved presently. And if you have that, then you basically have weakly coupled spin-1/2 triangles, right? So if you do a back of envelope pure-wise new field theory, you get exactly the same behavior. And you face the experiment very well.
Yeah, that's right.
So
yeah.
So I guess my question would be, how could you experimentally distinguish, let's say, mundane mechanism like what I just mentioned, which has symmetry breaking, and the mechanism we proposed here?
Yeah. So in fact, I was talking with Professor Bhaskaran a couple months ago when he was here. So he suggested me nuclear quadrupole resonance can be a very sensitive probe of this charge sector behavior. So, NQR, nuclear quadrupole resonance, measures the electric field gradient. So when there is a Plaquette electron, charge Plaquette order, so the local electric field gradient are modified. So there will be a signature in nuclear quadrupole resonance. And there's also, high resolution exoscale may be a good probe for the charge sector physics. By the way, I think the proposal, this mundane proposal of this trimerization of the spin-1/2 moment. In fact, I think there are this trimerization doesn't have to be from some kind of regular pattern. It can be any kind of trimerization pattern. There are infinite ways of. Did you see? Maybe I can explain to you later.
Actually, the funny thing is when you mentioned this effective KK Hamiltonian, it looks exactly the same as the effective Hamiltonian for trimerized triangular lattice. So because for each triangle spins 3 halves,
yeah, I understand.
You have 4 degenerate states,
yes,
right?
Yes.
And you have the exact same symmetry as the states just plotted.
Yes. So. Yeah, that's right.
Actually, I have a question about this Hamiltonian. So what is pi?
Yeah, pi is the linear superposition of Tx and Tz. So it's more like a compass, 120-degree compass model if I forget the spin sector. So that will be the 120-degree compass model if I forget about this. Yeah.
So your claim is that the ground state of this model is a U1 spin liquid.
The ground state of this model is not null actually. This is in the strong coupling regime. When the charges are strongly localized, then I should have this kind of model. But the exact ground state of this model, I actually don't know. But this model is highly fluctuated.
But that would be your claim, that this is the ground state is U1 spin liquid.
It could be. So the system might be in the intermediate coupling regime when you get a spin-on Fermi surface. Whether this strong coupling regime and weak intermediate coupling regime are smoothly connected or not, it's a question. Right?
So does the gauge field in the charge sector and spin sector talk to each other, or?
Say it again.
The gauge field in charge sector and in your spin sector, do they talk to each other?
Do they talk with each other?
Do they, like, for example, in your 2D case, you basically say you have this valence bond crystal because there is no gapless matter field interacting with your U1 gauge field in charge sector, right?
Mm-hmm.
But there are gapless matter field in the spin sector.
Mm-hmm.
Is there any way of?
It's a good question. Then there can be an indirect coupling. In fact, that's why I put a question mark. Actually, I put a question mark here. If there is no gapless spin-on field, the compact U1 gauge field in 2 dimensions is always confining. Yes. Polar coupling result. So the question mark is here means because there is a gapless spin-on field that will indirectly couple to this U1 charge gauge field. So it's not clear whether this thing should confining or not confining. So yeah. Yeah. Yes.
Okay, so if no further questions, let's thank the.
Yeah, thanks.